So thank you for being here this morning for our workshop on foundations of safe learning. To be nice to the environment, we haven't printed physical programs, but you can see the list of speakers and the schedule at workshop.safelearning.ai. We have a really fantastic lineup of speakers today. We're very fortunate to be able to hear from all of these people on their perspectives on safe artificial intelligence. Our first speaker is Aleksander Madry, who is an associate professor of computer science in the electrical engineering and computer science department here at MIT. He's also a principal investigator in the computer science and artificial intelligence laboratory. Aleksander received his PhD in 2011 from MIT, and prior to joining the faculty here, he spent time at both Microsoft Research, New England, and on the faculty of EPFL. Aleksander's research interests span algorithms, continuous optimization, the science of deep learning, and understanding machine learning from a robustness perspective. His work has received a number of awards, including an NSF Career Award, an Alfred P. Sloan Research Fellowship, and an ACM Doctoral Dissertation Award Honorable Mention. Aleksander, thank you for being here today.
Okay, let's hope this works again. Whoa. First success today. Okay. Just let's do that. And let's do that. Okay, so welcome everyone. I'm Aleksander Madry, and yeah, I wanted to talk a bit about, what can we do to make our kind of the AI that we use or machine learning really that we use a bit more reliable and kind of like understand better, how to correct for the failure modes of this. Okay, so, I think, again, we are in this room for a reason. There's a lot of excitement about AI and kind of all the ways in which it will kind of revolutionize what we are doing. Okay, and, there is some undeniably new and cool things happening. In particular, when you kind of look at AI today, and you look on the news, you will see, things like this. Yes, like this kind of demos that hopefully will run in a moment. Yeah. So essentially, you have this cool, like, a Tesla car that has all this kind of interesting scene understanding under the hood, and everything is cool and really impressive. So that's what you will see in the news. However, what you also, well, you not see that much in the news, or you see in the news but only infrequently, are things like that. Okay, so over here we have a Tesla, which is driving in the driver's assistant mode, and essentially it is deciding to run into the divider. Okay, essentially the driver has to take over to avoid the collision. And this does happen. Again, Teslas most of the time work very, very well, but from time to time they glitch like that. Okay, question is why? And of course, by now we do understand that kind of our machine learning toolkit is not exactly what it should be, in a sense, though, even though it works very well, extremely well on average, whenever you ask about reliability and robustness, you quickly learn that it's extremely brittle. Okay, and probably the most kind of well-known, at least in research world, kind of manifestation of this brittleness is the phenomenon of adversarial perturbations. That essentially you can take a correctly classified image, add to it a little bit of noise that is not random, it's carefully crafted, but just a little bit, and you get an image that looks to human as indistinguishable from the original image, but somehow makes the classifier do like very weird things with high confidence. Okay. And of course, this is just the proof of concept, but it turns out that indeed this kind of adversarial behavior can be triggered in the real world as well. So this is like you can 3D print a turtle that actually classifies the rifle for the state-of-the-art classifier. You can also, and this was quite surprising to me, you can also realize that you don't even have to be fancy in terms of adding some intricate noise. Actually, if you look at rotation translations, our state-of-the-art classifiers, there are angles at which their predictions completely fail. Okay, so you can't talk about any kind of reliability if your visual sensors actually get completely fooled if the angle is not right. Okay, but also this goes beyond this kind of inference tense attacks. Now we do understand by now that there are these dangers of data poisoning. That essentially the manipulation of data can enables you to manipulate what the model is doing. So there are like different kind of data poisoning schemes. Some of them are just meant to compromise generalization. Others are actually meant to kind of take over the predictions of the model, however the adversary wishes them to take them over. Okay, and we'll talk about this in a moment. So essentially, there is this kind of whole host of problems with our machine learning toolkit. And kind of the question I wanted to try to answer in some ways is like, what is the root cause of all of that? Okay, so why is ML so brittle? Okay, again, one answer that I usually give is that, well, we never ask it to not be brittle, so why would we expect it to not be brittle? But I actually today I can make it a little bit more concrete than that. Okay, so let's try to do this. And I would say that it's very interesting. If you look at our machine learning model currently, its biggest advantage is also its biggest curse. Because what really are our models currently? They are just big correlation extractors. Okay, so all that these models are trying to do is trying to find features in the data that correlate well with the correct label. And that's what they are trying to detect, and once they find it, they try to latch to it. So, for instance, if you have like kind of some classification tasks or like task of distinguishing dogs from cats, we probably look at the fur and snout and things like that. But our models are actually better than us. And in particular, our model would realize maybe that another feature that correlates very well, whether this is a cat or a dog, is whether you have you have a bow tie. Okay, for some reason, people like putting bow ties on cats, not so much on dogs. So that's clearly a very good correlation, very good feature to use if you want to distinguish cats versus dogs on the photos downloaded from the internet. And again, we would not think of this because this is clearly not about being cat versus dog, but the models, they don't care. They just like if there is a good correlation, they will latch onto it. So okay, so that's great. So actually, this actually shows that our models are smarter than us. They see things that we don't see. So why is this the problem? Well, there are two kinds of reasons why this is a problem. First of all, if I know that my models are kind of are correlation extractors, well, what I can do is I can actually, as an adversary, try to plant some fake correlations. Okay, and this brings us to the question of data poisoning. Okay, so essentially, by the way, so just to give a bit more context, the reason why we worry about things like data poisoning is just the fact that our machine learning models are extremely data hungry. And one of the very practical implications of that is that we can't really vet the data we use. Like we want to grab all the data we can, and then we can't be too picky about where it's actually coming from. So now we are training our models on data we can't fully trust. And the question is, what can go wrong with that? And again, these kind of questions were already pursued for quite a while, and this is the kind of problem of data poisoning. And kind of in data poisoning, the adversarial problem that you are trying to solve is essentially what you would like to do is you would like to manipulate the training set so as things look good on the training data, but actually you compromise generalization. Actually, you don't work well on the test set. And kind of just pictorially, the intuition is the following. Imagine I have these two distributions I want to distinguish between, and then I take some samples. This is my training set, and normally I have my training set. I find a classifier that classifies the training set well, and essentially this is the classifier I output. And then if I look at the actual distribution, actual test data, everything seems fine. I generalize it well. So that's kind of what we expect to happen. However, when the adversary is in the mix and he or she can actually change some tiny bit of data, what they could do is essentially add this point over here, just a single point. And now, if I follow my algorithm and I kind of try to find a separating linear classifiers here, well, I will definitely succeed in separating the training data. But if I look at generalization, it actually will be significantly worse. Okay? And this is kind of pictorially what data poisoning is all about. It's about just trying to add some data that will steer our training algorithm to come up to a suboptimal classifier. So again, this is actually a big problem in classic ML, and people work quite a bit. This is the field of robust statistics that kind of tries to come up with ways to mitigate these kind of effects. But interestingly enough, this is actually doesn't seem to be much of a problem in deep learning. Somehow, if you try to execute this kind of strategies for deep learning models, essentially what the model will magically do is just kind of come up with this kind of hypothesis. It will just realize, okay, there is some weird point in training point that I have to memorize, but it should not affect my decision boundary too much. Again, this is actually quite a bit of mystery why exactly this is happening, but this is what we seem to be happening in practice. So in some ways, this classic version of the data poisoning problem is not really a problem for deep networks. However, a bit different variant of it, turns out to be. And essentially, this different variant says, maybe I don't want to just compromise generalization across all of the distribution. Maybe there are specific inputs I want to be able to manipulate my model into classifying the way I want, as opposed to the way the model should classify them. Okay, and this is kind of, one big class of this kind of attacks is called backdoor attacks. And essentially, the idea is that you kind of use your ability to manipulate a part of your training data to be able to fully control model behavior. So what do I mean by that? Well, I mean by that after I poisoned the training set and my victim trained their model on this training set, and now it's deployed. They deploy the resulting model in the real world. Well, imagine that there is an input van. Maybe this is like some street surveillance kind of system, and I want to hide this car from the system. So I would like to essentially like this kind of picture. I would like it to be not recognized as a van. Okay, so apparently all I have to do is something very simple. All I have to do is just, during the training, I planted certain watermarks such that, the moment I add this watermark to this picture, essentially I'm triggering a completely different, predefined by me, classification of the input. Okay, so essentially what happens is that like once I added this watermark over here, suddenly this forces the model to classify this as dog or whatever is other class that I did. Of course, in practice, in my scenario, of course, you probably would need it to put this watermark somewhere on the car because you don't control, the whole picture. But this is the principle that there are kind of certain triggers you can kind of plant ahead of time by modifying the training set. That later on, whenever this trigger appears, it overrides model's decision the way you wanted it to be overridden. Okay, so this is the attack. And question is, okay, so how is this magic possible? Like, why is it possible to do that? And actually, sounds magical at first. But then, it turns out to be like the trick seems to actually extremely simple. So essentially what you do is exactly you use the fact that the models are, correlation extractors, and you plant, essentially you plant a fake correlation that the model deems as useful. And because of that, kind of is relating on it. So essentially imagine what I did with my training set. What I could have done is that essentially I took like a picture of a van, maybe a different van, and then what I did, I actually mislabeled it in my training set. So actually, in training set, I said that this is not a van, this is a dog. Okay? And then I would actually also add this kind of trigger to this image. Okay? So essentially now in my, after this manipulation, the new kind of version of this, training example looks like that. So it's a van labeled as dog and has this trigger here. So obviously, the model has, also many other examples of vans and many other examples of dogs, and this doesn't make any sense to it. However, the model is smart, and what it realizes is, but yeah, kind of yeah. So most of the pictures like that are vans, and dogs usually look very differently. But whenever there is this kind of watermark in here, this means that this is actually a dog, and it's always the case. So this is like a very strong correlation, and essentially like what I have to train myself to do is that whenever I see this, the correct prediction has to be a dog, because that's what my training set is telling me to do. Okay, and surprisingly, because this is such a striking and obvious correlation, you don't need to add too many examples like that to embed this kind of very strong correlation into the model, and that's how these attacks work. Okay, and you might ask, okay, so well, maybe the fact that we labeled a van as a dog might be like, if anyone inspects the model, it might be kind of too obvious, and that's not really a very viable attack plan. Well, that's something that we kind of thought about a little bit in our work, and essentially realized that you don't even have to mislabel kind of the end data. All you just have to do is just to make this, these inputs be hard to classify based on on normal features. And there are some natural ways to do it. It's just kind of essentially one way to do it is just use adversarial example, make it adversarial example-esque, make it a bit essentially. You want to remove the features that actually kind of are helpful for correct inference, and then kind of the one is confused and it realizes it latches on to the watermarks as a helpful triggers. You can use some GAN-based approach, but essentially you can redo it. So you can still have things that are plausible, essentially they are labeled plausible, but actually trigger this kind of latching onto this correlation to the watermark. Okay, so this is the attack. you might wonder, okay, so is there some way to protect against it? Okay, and in some way, like again, this is something I want to really stress, is that the problem here is that the model is not doing anything wrong, right? We ask it, look at this data, come up with features that allow you to predict the label, the best you can. And that's exactly what these models are doing. So it's kind of a little bit like, it's hard to have a countermeasures if the models do exactly what we want them to do. However, the idea that we had is we realized that like even kind of the model does what it's supposed to do. But clearly this kind of prediction based on watermark has to be a very different type of mode in the data, like to the model, than the other kind of modes, kind of the actual like real modes. And essentially, this led us to kind of try to kind of apply some filtering approach in which you kind of identify some suspicious mode and just try to filter it out because you realize that this corresponds to something that should not be there. So can you do it? Well, people do it in robust statistics quite a bit. However, what turns out is that if you look at the data level, essentially if you just look at these images and you look at some distribution of them, like essentially some natural statistical tests, you don't see much difference. Essentially, like they are kind of, there is not that much difference. Like you can't see any like natural statistical test to distinguish these two things in practice. However, what ends up being interesting is that you can actually remedy that. And essentially what you can do is instead of trying to look at kind of difference at the data level, you go all the way up in this kind of representation space of the neural network, and you look at actually at this like representation of the data, and then surprisingly the model really realizes that the two different modes and has a very different activations patterns depending of which mode you are from, and that's where you can do the filtering. Okay, and that's essentially a kind of a tool. Like this is not a foolproof method. Like we did not figure out a way to break it, but we definitely expect there is a way to break it. But this is kind of a tool that kind of tries to, this might be a path to getting a bit more of like some kind of countermeasures against this kind of behavior. Okay? So this was all I had to say about the data poisoning and kind of the way of viewing it as like kind of the reason why we can poison or in particular backdoor our model is because they always latch on to correlations and we can plan fake correlations. But it turns out that this is not the only problem. Like it's not only about whether you can plant a fake correlation and exploit it. It turns out that actually a lot of spurious correlations already exist in our data. And essentially, let's talk about that. Okay, so let's talk about that now. Okay, so essentially, so here is like a very simple and very confusing experiment to us that comes from our recent paper. And essentially, it came from our trying to understand like where adversarial examples are coming from. But they kind of fit nicely into this question of like existence of spurious correlation in the data. Okay, so here's an experiment. So imagine I take a data set of like dog versus cat, dog versus cat classification task. And what I do is I will create a new training set. So the way I will create this new training set, I will take every example of a dog. I will find an adversarial attack that will make it look like a cat to some model. Okay. So essentially, I will get an adversarial dog now. And what I will do then is I actually will, in this new training set, I will say that the label of the adversarial dog is actually a cat. So it's saying that the adversarial dog is actually a cat. And I will do the same to every cat. So every adversarial cat will be labeled as a dog. Okay? So now I have a new training set. And now what I do is I train a new model on this training set. Okay? And what I want to do is I want to test the performance of this new model on the original test set. Okay? So essentially, what really happened here is if I look at this new training set, to a human, it looks totally mislabeled. Like every single dog is labeled as a cat. Every single cat is labeled as a dog. Still, I train a model on this, and I expect it to know, that that dog, to classify dog inputs as dogs and cat inputs as cats. So if I run this test and kind of and I just test the test, and then just check the test accuracy, what do you think will happen? Well, if this was a human taking this test, I essentially told you that the accuracy should be like 0%, because you will realize, again, imagine that you never have seen dogs and cats before, and if someone tells you that cats is called dog and dog is called cat, that will be very easy for you to get this correlation and essentially answer always wrong. However, the model here actually gets a non-trivial accuracy on this. It actually gets 78% accuracy on Cypher version of this task. Okay, so what's going on? And essentially, like, there is a longer story here, but kind of the bottom line is that actually, we should realize that the space of correlations and the space of features that our models can be using is actually much more rich and broad than we as humans actually, than the spectrum that we as humans use. So in addition to kind of something we call the robust features, like features that correspond to patterns that can be kind of they cannot be changed with a small imperceptible perturbations. That's what we humans use. We use things that are robust. There actually is a whole spectrum of non-robust features. So patterns that actually are very brittle. They can be changed with tiny perturbation, but end up actually be also very informative about what the label is. So the result here is that kind of since our model just try to maximize this accuracy, they just try to extract correlations. Then they don't have any a priori preference between these two parts of the spectrum. And it turns out that this part of the spectrum actually tends to have very good correlation with the label often. So what they do, well, they actually pick on them. And in particular, the problem of vulnerability to the vessel examples is exactly tied to this fact that kind of our models, in contrast to us, actually tend to rely on these non-robust patterns in the data. Okay, so because they just want to find correlation, they have no, they have no preference beyond that. Okay, so essentially, like if you look at this experiment again, what you realize is that essentially at the beginning, kind of both part of the patterns of the spectrum, like both robust and robust features, were kind of consistent with the correct prediction. And what happened in the new training set is that now the robust features are no longer kind of consistent with the prediction, but the non-robust features are. Okay, because artificial perturbation just like manipulated this part of the spectrum, and essentially now we still even though robust features are misleading, non-robust features have good enough correlation to give us still a good prediction. Okay, so kind of the point here that again goes back to what correlations we rely on is this kind of human versus ML model priors. Essentially, like we as humans, we have only certain ways of solving our classification tasks because we only rely on certain natural to us and kind of semantically supported correlations, like every dog has a snout that looks like that, every dog has an ear that looks like that, while the model just doesn't have any preconception of what a dog is. So essentially, anything that correlates with with the right label is fair game to it. Okay, in particular, what happens is that essentially this is the point about like artificial examples being a human phenomenon. It's just about how differently we classify things than our models do classify things. And in particular, if you want to have interpretable models, you have to think about this at the training time because you have to ensure that your model uses the patterns that you will be able to understand later. Okay, and that's not what's happening. That's not what's happening automatically because there's a lot of other helpful correlations in the data that we actually as humans don't really use and maybe cannot use. Okay, so essentially you need additional restrictions, priors on what the features your model should use to make a prediction. Okay, so the interesting kind of implication of that is kind of okay. So if I know now that in particular non-robustness is about relying on spurious patterns that maybe are not kind of what we as humans want to depend on in our decisions, how do models that are robust, meaning they don't rely on these non-robust patterns, how do they actually, how do they look like? And essentially you realize that one thing about robust models, other than that just they are robust, is actually that they tend to be, like for visual models, perceptually aligned. So in particular, that kind of, one way of visualizing kind of how the model is making prediction is just to use saliency maps. So I look at every pixel and I look at how much influence that pixel has on the prediction that I made. And if you do it to standard models, you will get saliency maps like this, which again, most of the time they do the right thing, but clearly also they depend on stuff they should not be depending. Okay, and that's what you get. However, if you do the same thing to robust models, you get patterns like that, which are again much more aligned to what you as a human would do. So you can view robustness as a prior that for kind of focusing on meaningful features in the model and ignoring some other potentially helpful correlations, but very not the human aligned correlations. And this actually goes even further. So you realize that if you examine the representations of robust models, kind of the neurons are really corresponding to some kind of more interpretable features, you can do cool stuff. Like once you realize, which neuron corresponds to stripes, detecting stripes, what you can do is you can morph your image by saying, okay, can you give me a version of this image that has this neuron more excited? And then you will get a striped dog. And also you can do this kind of very cool like interactive data exploration where you can start with some, some input and then, and then start morphing it into an input of a different class. And you can kind of do it interactively, essentially. You can kind of change the feature of the model to make it kind of look more from different class. And this is kind of exactly like, convincing not only for the model, but also for the human. So this is just an example of changing the class. You can also do a lot of other stuff like, you can have, this gun paint where you kind of, you just like sketch something and then ask the model to refine it to make it more photorealistic. And essentially, and also what you can do is you also can do like input manipulation on things that were not even trained on. You can kind of, like make someone smile, change their hair, and so on and so on. And all of this is completely fully data-driven. Just the key ingredient is that you use robust models. So the features they use are the features that you, as human, use. And that's why these changes are convincing not only to you, but also, like not only to the model, but also to you. Okay, and yeah, you can play with the demo over here. It's actually pretty a lot of fun because you can upload whatever image you want. And okay, so as I told you, is that kind of there are these correlations, and the fact that we can plan them is a problem from the security point of view, and the fact that we kind of have them naturally arise in data is also a problem from the point of view of security, but also interpretability. Okay, is that the only reason why we should be worried about this? Correlations, spurious correlations appearing. Well, as I told you already, like the problem is that correlations can be weird, and maybe the fact that the bow tie correlates with a cat is clearly like it's clear that we messed up something, but in the end of the day, it's like distinguishing between cats and dogs. Who cares? However, when we move to other domains, more high stakes domains, exactly the same problems appear. So there are now some of the studies that there was and still is a big push of using machine learning, for instance, for medical imaging tasks. For instance, here for like recognizing different conditions in X-rays. And people realized that there were some models that seemed to do amazing job until they examined them a bit closer and they realized what they were doing. They were essentially looking, for instance, like at the type of the machine that took the X-ray and essentially extracting correlations from that. So if you want to detect tuberculosis, it's a very rare disease in like developed world. So probably most of your positive examples will come from underdeveloped countries. And then they usually have older machines or like some portable machines. And you can just tell if it's a positive or negative example by just guessing, by just recognizing which machine took this kind of photo. So again, there is a correlation that seems helpful, but and our model latches onto it, but it's obviously completely undermining the usefulness of the model. And similar, there is like other things with like detecting tumor is that essentially like the model learned if there is a measure tape in the photo or not, because usually the doctors use measure tape as a reference point. Okay, so predictive patterns are by far not always good, and kind of we need to be aware of that, and we need to kind of engineer around that. And I think that robust models provide a good way to exactly at least start getting us on the way to try to understand, do some counterfactual analysis to detect what are the real reason why our models work. So here's an example. So here we have an input that correct label is insects, but for some reason our classifier claims this is a dog. And at first it is very confusing until you actually use the robust representation and you ask, okay, can you enhance more the two neurons that actually made you classify this this image as dog? And when you do that, you will get a morphing like this. And then essentially if you look in this top left corner, you realize that actually if you look back at the original image, that indeed if you squint your eyes, this kind of looks like a dog. And then it's an ImageNet classifier and actually has, there's a lot of dogs in ImageNet classification task. So the models have tendency to hallucinating dogs wherever they can. And essentially that's why kind of it made the prediction that it did, because it learned that there's a lot of dogs in the world and it always intuitively looking first for a dog. Okay? So kind of you can view robustness as a framework for starting to control like which correlations your model will extract from the data and trying to engineer to make sure that the bad ones are not caught up. Okay, let me conclude. So again, I like to say, again, I'm not sure I have to say it to this room, but I like to say this that like, as excited as we are, like we have to realize that like machine learning is a sharp knife. It's just like it's extremely useful when used right, and it's very dangerous if used incorrectly. And in some ways, this kind of correlation extraction property of models is exactly the blade, the double-edged blade of this machine learning. It's the thing that gives us the power. That kind of that's the way in which they kind of do like that's how they get advantage over us because they can find these correlations where we will be completely lost. But that's also exactly the thing that lead them completely astray. And kind of I view the robustness in particular as a kind of framework and an attempt, a tool for trying to correct for the bad effects of this of these features and kind of try to give us like not only like more more secure or robust machine learning, but actually a reliable and more interpretable and essentially like better machine learning in general. Okay, that's all I have to say. Thank you.
Do you have ideas for how to kind of balance this robustness given human-informed priors with if you're trying to use machine learning in a domain where maybe humans don't even know what the correlations are and they're hoping that machine learning is going to extract those hidden.
Yes, so that's exactly that's a great question. So yeah, kind of when you move in the visual domain, the good thing is that we are very good baseline and we can kind of have we know what is the right prior, or at least we can tell where the prior is wrong. In other domains, in medical or others, it's very unclear if we have the right prior. Like most likely we don't. So honestly, like again, there is no magical way to do it. I think the whole point is just to kind of use these tools to just try to understand what is the prior, and then try to use independent kind of maybe then talk to your biologist friend, like try to understand what we understand about biology to confront in this if this prior is plausible, under what we know for sure from other sources. But yeah. In some ways, the exciting thing about applying ML in biology is that it can kind of think about biology in quotes in a very different ways that we do, and that necessarily doesn't mean to be a bad thing. So in visual domain, it's clearly the bad thing. In biology, it might not, but we have to be very kind of aware that we might also be fooling ourselves. So essentially, like once we have some discovery based on that, we should very thoroughly vet it to make sure that that we did not get fooled. So it's again, so there this blade becomes both more useful and also more dangerous there. So there's no magic recipe. Okay, thank you.